Okay, so yeah, my name is Sermanoukian and I'm part of the Navigation Support Office team. And today I will be showing you our progress on enhancing ESA's combination at the observation level. First of all, I would also like to acknowledge all the work of our team. Yep. So first of all, we'll start with what the combination at the observation level is. Then we'll go for the orbit comparisons, and then we'll also compare it against the normal equation stacking. And then later on, we'll see what are the effects on the Earth orientation parameters, the geocenter motion approximation that we are doing, the terrestrial scale, and we will summarize with the conclusions. So, first of all, what we call the combination at the observation level, or COOL for our acronym, and the main objective is to combine all four geodetic techniques together in one single processing run. How we do it? We do it in order to benefit for the strengths of each technique while tackling the inefficiencies and detecting and reducing these technique-specific systematics. And that we do not only at the observation level, but we can also on top add additional normal equation stacking. And in order to do this, we do it on our ESA Precise Navigation System, or EPNS, which is the software that we are preparing and also with the knowledge in order to processly routine Genesis, not just because it's cool, but because we need it. And as such, we go first of all for the GNSS, then SLR, DORIS, and BLBI. So you might ask, okay, where are we right now? So the current status is up to step 3. We've managed to do it. We started with the GNSS and Sentinel satellites, firstly tackling Galileo and GPS processing, and following up to the multi-GNSS processing, which we do as part of our IGS AC contribution. Then on top, we've also added the SLR to Galileo, Sentinel, and ILRS targets, the first two at the observation level, and then the ILRS target at the normal equation level. And similarly for DORIS, we've tackled the Sentinel observations on top at the observation level, but we can also add not just Sentinel, but other satellites from our IDS contribution on top to see what are the effects of this. So for this, just a summary of all the satellites that we are using right now. These were the ones mostly available in 2024. And you can see in the dark blue ones our main constellations, followed by the Sentinels, where we are mostly interested right now in Sentinel-6A, because it provides not only GPS observations, but also Galileo. But then also on top, we add the Sentinel-3A and 3B, which allows us even more data for GPS. The red ones are part of the IDS contribution and the green ones for the ILRS. And as you can see, we have plenty of different orbits and plenty of different satellites. In this case, just give or take around 124 satellites. And yeah, each of them have their own different measurement types, but we are mostly interested, as we said, onto Sentinel-6A and 3A and 3B, but we are always open to do these different combinations. As I said before, right now we are using our EPNS software, and the models and reference frames are mostly the same ones we use for our contribution to as AGSAC. But on top, we have our Sentinel corrections from the ESA Sentinel Antex, but with the change of the S213 Antex scale. And as part of the observations that we'll be showing on the next results, we have the first couple of months of 2024, for which we have an arc length of 24 hours in general, which can also be stacked up to a week. And we use up to 200 stations for GNSS, 30 for SLR, and 60 for DORIS. And also the sampling can be somewhere between 300 and 30 seconds. And just to show you a bit the distribution of the reference stations, partly some IGS core stations, but also on top SLR and DORIS in order to be able to do the specific transformations later on. So let's dive deep into the results. What we've seen so far in here, we have the standalone solutions, so Galileo and GPS on blue. And the first thing that we can see already is that all combinations either improve or at least maintain the 3D RMS values over these 60 days. If we go more into detail, we can see that just adding, for instance, SLR on Galileo does not really improve that much our orbit, most probably because the number of observations is really low compared to all the other combinations. However, we see that just adding one LEO, in this case Sentinel-6A, based on also only Galileo observations, can already give us an improvement almost of 10% in these orbit overlaps, which we are taking as the worst metric that can be computed in order to analyze this internal consistency. And we can see that even adding on top the Doris and SLR observations more or less maintains the same results, even though we see some intricacies that slightly degraded from the GNSS only solutions. Something that is also interesting is that just basing Sentinel-6 on Doris data or Doris and SLR still gets more or less around the same values that we were having. That is something that we are still looking into. And so far, the best solutions that we get are when we process together the Galileo and GPS so that they result in the best agreement. We can see up to almost 20% improvement from the initial standalone solutions, which is really good. It's computationally demanding, but for finals and so on, it's pretty interesting. And on the right-hand side, we can see the same analysis for GPS, where we have similar results for Sentinel-6 only, and this here on top, we've also added Sentinel-3A and Sentinel-3B. However, while we have the same results for GNSS, in here we've seen some inconsistencies, mostly when we add either Doris or SLR on top, where you get a degradation on the results. They are still better than the standalone solution, but there's something that it's not quite matching. And yeah, in the same way, when we combine this with Galileo, we get the best results so far. Looking then into the LEOs, so Sentinel-6, 3A, and 3B, we see similar results. We can get that when we compare all the solutions against our typical PPP, we see that almost all of them are either better in this case. The best scenario in this case we can see for Sentinel-3B, when we go to almost half the orbit overlap that we get from PPP doing this cool combination. And yeah, in that sense, we can see that even though we can get some similar results when only using GPS for Sentinel-6, once we use the Galileo observations, we get much better agreement. However, when we use both Galileo and GPS on top of the orbiting receiver for Sentinel-6 is again where we get the best agreement so far, meaning that also the biases and everything we are handling are quite correctly set up, but we can probably still see some improvements from the previous presentations we had so far. And yeah, we can see also it's interesting that while we were expecting for 3A and 3B to have more or less comparable results, we still see quite differences that are still being researched in our team. Then going against the cool, against the normal equation, which is something quite popular in the last few days, we see that all our solutions on the cool level are improving. However, this is not the case when we do it at the normal equation level for all solutions. In this case, Galileo, as we can see on the red and light green solutions, get slightly worse overlaps when we do it at the normal equation level, probably for these independent station clocks or other parameters that are not properly matching. However, this is not the case for GPS, where we see that we still get an improvement, meaning that it's not always not beneficial for the satellites. But yeah, it's not the same as just doing everything on the observation level. And what we've looked at is that it's not really some specific satellites of each constellation that we're maybe downgrading the solution, but something that affects the solution altogether at the same time. So there's no clear specific satellite modeling. Something that affects the whole constellation is most probably the reason behind. Then looking at just a glimpse of the Earth orientation parameters with respect to our reference, which is the IRS EOP 2004, we can see the different comparisons in order for external consistency. And in here we have both Galileo and GPS. So dark blue, we have our GPS, Galileo, only solution, and audit on top the SLR observations. Well, before we were saying that there's not that much effect here, we see that we get a better agreement with the EOP 2004 in terms of a bias, not so much in standard deviation, that remains more or less the same, but it's also interesting to see that adding the Sentinel-6 observations doesn't really harm. It's more or less around the same value within the noise. It's also interesting that then when we add these solutions and stack them at the normal equation level with our ILRS ESA solution, we get quite some bias for the Galileo only, but this is somehow fixed when adding either SLR or any of the Sentinel-6 solutions. And more or less similarly when we stack it with our IDS contribution, in this case removing the Sentinel-specific and just adding on top the non-contiguous satellites. And yeah, then going again, we go GPS, which is interestingly on the other side of the bias. So while we have one is positive, the other is negative, but we see some similar conclusions for the light blue and the yellow cases, where it's adding either Sentinel-3A or Sentinel-3B. And our best solution again comes from adding Galileo GPS, and probably we can add Sentinel-6 or not, but that doesn't really harm or benefit our solution. Similarly, what we did for the geocenter motion approximation is that considering the origin of the ITRF 2020 update 2023 as a reference geocenter, we get two different solutions. One where we do the no net translation, no net rotation, and free scaling, and on the other one we allow free translation in order to see how much this origin is changing. It's also important to highlight here that for the alignment, we're basing it on the IGS 20 core stations and the extended ILRS list that I showed before on the map. And we can see here that just going, for instance, on the Galileo, which is the blue on the left side of the plot, we can get an improvement that goes closer to the target RMS, which we are basing on the annual expected geocenter motion, considering a 26-year weekly Lagios 1 and 2 SLR series from Yu et al. And we can see that either adding SLR or Sentinel-6 or anything else not only improves the specific bias, but also the standard deviation is reduced as such. And then when adding on the right-hand side ILRS, we can see that we have a similar improvement, but we can see that adding at the normal equation level, this solution does have a huge impact in the bias, where we even go below the expected RMS that we were expecting, which means that we have to take into account some of the things in the normal equation stacked weighting or something else that we are right now not taking into account. Then we have our scale comparison, which we do a similar thing, but we just fix on one case the stations, and then we use the same reference solution that we were getting, and then we compare how much the scale is changing in between. And we compare it on equal weighting for all the stations of GNSS, SLR, and DORINS, where applicable, of course, with the removals of outliers beyond 3 sigma. And what we can see is that, of course, there are some already biases on Galileo and GPS, which we can explain because they are consistent with the use of our ISA-23 antex and the different Galileo set PCOs. But on top, we see that the effect of SLR seems to be quite minimized. So probably meaning of the low number of observations, and we would have to somehow artificially increase this weight in order to get some benefits in the radial direction. But also on top, the Sentinel-6A alone does not contribute much, except when it's using all the different observables, so GNSS, SLR, and DORIS, where we see that this bias is reduced. However, the standard deviation is increased, meaning that it's not just a really good benefit overall. We have more or less the same for GPS, and again, we have a combination of Galileo and GPS, which is somewhere in between. So for the conclusions and the next steps, we've seen that our software can properly combine GNSS, SLR, and DORIS observations, both at the observation level and at their normal equation level, allowing a modular design so that we can get the best of both worlds in this case, tackling what one can do best and also showing us what the other cannot in order to improve it somehow. And as such, with what I showed, the methodology allows us to improve the internal consistency of the Galileo and GPS orbits, allows to maintain or improve also the Earth orientation parameters agreement with external references like IRS, then improve the geocenter consistency with the ITRF while reducing this uncertainty and maintaining at least the terrestrial scale difference stable with respect to the ITRF coordinates across the solutions. We've spotted, as I showed, some inconsistencies between cool and next stacking that we should tackle for the next results. And something also interesting on top from previous presentations is that DORIS observations seem to be only mostly good in addition of something else. So when adding GNSS and then DORIS, but DORIS alone seems to harm at least on our orbital site. And we've also seen that for ILRS and IDS, the external inputs gives us quite an insight of how to approach this in the future, not only within our team, but also in combining the benefits and drawbacks of this independent normal equation stacking. And for our next steps, we want to understand and hopefully solve these inconsistencies that we've shown so far. And we are also working on the BLBI integration along with the active development of this within our software so that we are quite ready when Genesis is launched and we can have some quite results. So yeah, this is all. Thank you very much.